The force that holds us all from floating off in space also keeps us in constant motion. Motion that sets the stage for stellar phenomena. The force? Gravity. The mutual attraction to anything with mass causes the galaxy to move and push itself. Our entire solar system was formed because of this motion. From interstellar gas and dust particles that moved toward each other, collided, and eventually started spinning. This spinning is full of variation and irregularity, but at moments all these variables can come together just in the right way for something rare and beautiful. Let's take a look at how this occurs. To do this, we must look at the variability of rotations and orbits. A rotation is when an object spins on an axis like a top, while an orbit is the movement of one object around another. For example, the Earth rotates around its axis. Our only natural satellite, the Moon, orbits around the Earth. It has a synchronous rotation, meaning the same side of the Moon is always facing towards Earth. Earth's satellite system orbits, or revolves, around the Sun, a star in the middle of our solar system. Our entire solar system is also in movement as it orbits around the Milky Way galaxy. Due to the spinning motion of how it was formed, most of the solar system is a relatively flat disk in space, but it's not perfect. In relation to the angle of Earth's revolution around the Sun, known as Earth's orbital plane, the Moon's tilt, or orbital inclination, is 5 degrees. Without this tilt in its orbit, the Moon would otherwise cause solar eclipses monthly as it orbits between the Sun and Earth. These orbits are all elliptical, meaning their paths are shaped like ovals, known as ellipses. They also change eccentricity, or shape, meaning that the Moon and Earth, and the Earth and Sun, are not always the same distance away from each other. However, Earth's revolution around the Sun, like most of the planets in our solar system, is nearly circular with only small variations. The Moon's elliptical orbit results in the Moon being anywhere from 221 to 252,000 miles away from Earth. This means that from Earth's perspective, the Moon's apparent size in the sky can change by 13%. Both the Moon's orbit around the Earth and the Earth's orbit around the Sun are not fixed either, rotating the orientation of the orbit in what is known as apsidal precession. Earth's rotation also tilts and wobbles compared to its orbital plane and rotational axis. This tilt, or obliquity, is currently at 23.4 degrees, but changes over time. All of this contributes to when, where, and how the Sun, Moon, and Earth align in space. Since some of these motions vary, that is why eclipses can happen all over the Earth at different times of the year and at inconsistent intervals. Since all these variables are measurable, it allows us to predict them. Anytime 3 objects align in space, the middle object appears to transit between one object and the other. From Earth, we commonly see shadows on the Moon, but this is not always a transit. Most of the time, it is from the angle of the Sun and our perspective of it from Earth. These shadows happen at regular intervals known as moon phases. Since full moons and new moons are when the Earth, Moon, and Sun are aligned, this is the only time these types of transits can occur. When the Earth transits between the Sun and the Moon, it causes a lunar eclipse, where an otherwise full moon is blocked by the shadow of the Earth. Lunar eclipses are observable by anyone on the side of the Earth facing the Moon. When a new moon transits between the Sun and Earth, it causes a solar eclipse. And depending on its orbital inclination and eccentricity, it can appear as a partial, annular, total, or hybrid eclipse. Most commonly, the Moon's orbit does not align perfectly for a total eclipse to be viewed. When the Moon only passes in front of some of the Sun, this is called a partial eclipse. When the Moon is farther away in its orbit, its apparent size is not always big enough in the sky to fully eclipse the Sun, causing there to be a ring of fire effect. This is an annular eclipse. When the Moon is closer to the Earth in its orbit, it can fully shroud the Sun, giving us a total solar eclipse. But all of these variables of motion and placement have to align just right for this to happen. The places that can observe the total eclipse form a line called the path of totality, with deviation on either side from the path resulting in a partial eclipse. The path of totality can be seen from space as the shadow of the Moon moves across the surface of Earth. When you find yourself in the path of totality, take the moment to enjoy the experience. Focus on the sights, sounds, and feelings caused by the eclipse. A hybrid eclipse is the rarest of all because it adds one more variable. It occurs during the time the Moon is transitioning from being too far to eclipse the Sun to being close enough, or vice versa. This causes some places to observe an annular, others to observe a total eclipse, and even more to view a partial eclipse. Observing eclipses allows us to learn more about the Sun, Moon, and our place on the Earth. Before the invention of the telescope, observing lunar eclipses was used to accurately chart longitude on Earth. With modern telescopes, solar eclipses allow us to observe the Sun's corona, part of the Sun's atmosphere. The corona is usually too dim compared to the rest of the Sun to safely study. Other transits happen much more frequently than solar and lunar eclipses on Earth. Many of our human-made satellites transit in front of the Moon and Sun. Other transits happen less frequently, such as the transit of Mercury or Venus in front of the Sun. When observing things in the sky, we rely a lot on light being produced by stars and their reflections. But transits allow us to observe space by using the absence or fluctuation of light caused by objects moving in front of light sources. Most exoplanets, planets not in our solar system, have been discovered using this method. We can measure the amount of light a neighboring star produces, and when the star dims, we know something is passing in between it and the Earth. Based on how much light the exoplanet dims, we can determine the size of the planet, while the time between dimmings can tell us how long the period or the time it takes to orbit is. During the transit, we can also analyze the dispersion of light that passes through its atmosphere to learn more about its composition. Along with knowing the temperature of the star, discovering the size of the orbit and atmospheric composition allows us to gain insight into the habitability of the planet and whether there are conditions able to sustain life. Observing transits at any time, whether during an eclipse or not, allows us to learn more about our galaxy and how it works. Solar eclipses are rare, and each one is an opportunity to learn more about ourselves by furthering our understanding of space and its possible habitability beyond Earth.